Good morning, everyone. I'm here to introduce Rafal Wojtczuk. He's given the talk on analysis of the attack surface of Windows 10 virtualization-based security. You are in, which room is this? I forgot. Anyway, stop by the business hall located in Bayside AB. The Black Hat Arsenal is on the Palm Foyer on level 3. That's the same as, that's the one upstairs. The course of Arsenal reception at 1700. If you haven't picked up your merchandise, today is the last day for the store. Visit the Kali Linux Lab in Mandalay Bay 8. And thanks, as always, for putting your phone on vibrate. Good luck, Rafal.
Thank you, my guardian angel. Good morning, everyone. So what shall we talk about today? So we'll start with a short introduction to VBS architecture. Then we'll talk about Credential Guard and hypervisor-enforced code integrity, about their properties and internals. And these two topics will be covered under assumption that an underlying hypervisor has not been breached. And we'll cover the topic of Hyper-V security later. Again, we are mostly interested in the complexity of the solution and the attack surface. So I will be talking about attacks that work, that potentially work, and that do not work as well, because each teaches you something, right? And generally, more details are in the white paper, so if you are interested in more details, have a look. Scope, most of this research was done with Windows 10 15.11, so no, it's not about anniversary update, sorry. It's about Intel's hardware when relevant, and there is mixed origin, little known, and for completeness, well-known content. Okay, so VBS architecture. I sincerely hope that most of you are familiar with the concept, because if you don't, it will be probably difficult to follow the presentation, but as an introduction. So when Hyper-V is installed and virtualization-based security enabled, Windows 10 operating system no longer has full control over the whole machine. Instead, it is running within a VM, within a virtual machine. It's named root partition or VTL0. And as any virtual machine, it is subject to a number of restrictions. For instance, it is the EPT table, which is structure maintained by the hypervisor, that dictates whether a given physical memory is readable, writable, or executable. It's no longer under control of the kernel. There is another VM created automatically. It's named VTL1. And it has its own kernel. It has its own user mode. And its purpose is to enforce policies, security policies, as well as to provide a set of services to the root partition. And why all this trouble? Because the threat model is that Windows operating system has been compromised up to the point of malware possessing kernel privileges. So you no longer can expect the Windows kernel to enforce security policies because it has been compromised. You need something external, more privileged. And finally, beware that all this VBS is about preventing or limiting very specific set of attacks, right? Many actions typical for malware, like exfiltrating sensitive data or ransomware or connecting to internal network, are not abstracted in any way, right? So this is solution just for a couple of selected attacks. Okay, so the first item is Credential Guard. So the idea is that Credential Guard is supposed to prevent pass-the-hash attacks. So without Credential Guard, in LSASS process, in the Windows operating system, in its memory, the hashes of the passwords are kept, at least for the duration of the logon session, so that the single sign-on can work, right? And the problem is that attacker can steal these hashes, right? Extract them from LSASS memory, and then use them to authenticate remote servers. So the idea behind Credential Guard is that this time, these clear secrets, authenticators, are stored not in LSASS, but elsewhere, within this protected VTL1 virtual machine. And LSASS only holds encrypted version, right? So let's see how it works. Particularly if you run Mimikatz on Credential Guard protected box, you no longer can see NTLM hashes, right? you can see that all it can get is some large binary blob, and it says it's LSA isolated data. Yeah, so that's nice. Okay, so let's have a look at details. So there are different possible configurations related to Credential Guard. And the first one is that what happens if admins just enable Credential Guard in the group policy? So just tick a single box in the dialog, no further hardening, right? It's nice, easy to deploy. So let's see what are the properties of that scenario. So Credential Guard main process is named LSA ISO. It runs in this protected VTL1 machine, and it exposes RPC interface over some ALPC port. And this is the list of all the methods available to LSASS. And LSASS talks over this RPC interface extensively. And the most interesting methods are these two, protect credentials. So this is used during the logon. So when LSASS receives credentials during the logon, it passes it to LSA ISO over RPC, and LSA ISO responds with encrypted credentials. And from this moment on, LSASS can just discard all the plaintext authenticators and just keep the encrypted version. So how to use it? Another example is get NTLM3 challenge response. So whenever authenticators are actually needed, right, for instance, to compute NTLM response, again, LSASS must talk over RPC to LSA ISO. And in this case, it passes the blob with encrypted credentials received in the previous step, plus NTLM challenge, username, etc., anything that's needed to compute NTLM response. And LSA ISO is capable of decrypting the credentials, right, because it has the key, and then use it to compute NTLM response. And then it passes back NTLM response to LSASS, so it can send it to the server. So that is how it essentially works. So what are the properties? Again, after logon, no clear text credentials in LSASS. That's good. Still, while user is logged in, LSASS will authenticate remote servers automatically via using this RPC mechanism. But the problem is for attacker as well, right? If someone has compromised the machine and runs code as the user, attacker will be authenticated as well. Even more interesting is that if attacker collects encrypted blob, then he can still use directly RPC interface to Credential Guard and still authenticate as the user, even after the user has logged out. So this is more interesting. And let's have a look at demonstration. Maybe it will make it clear. Okay, so what we see here is the victim point of view. So it has logged to some Windows machine. It is logged as domain admin. And this is attacker point of view. So attacker already has compromised this machine and received connect back shell, and it runs with privileges of system user. So as we can see from task list, LSA ISO is running, so Credential Guard is enabled. So what we will do, we will inject a DLL into LSASS process in order to monitor the RPC traffic to Credential Guard. To monitor it and also to mess with it to some extent. So we can just inject the DLL. Okay. So now let's see some user is still logged on. So what we can do, we can just steal a token, right? So retrieve a token from an existing process, for instance, from Explorer exe, and once we do it, we run our process as logged in user, right? From the point of view of the operating system, we are the logged in user, right? And because this user is still logged in, we can just use his credentials to authenticate to any remote server, right? Again, operating system thinks we are the logged in user. Okay, so that was expected. So now let's try to do something more complicated. Okay, let's have a look at the logs our injected code has produced. So we'll see that it's capable of collecting the binary blob, this encrypted credentials. We can see this encrypted credentials has been written to this particular file. And we can see that different RPC methods had been invoked. Okay, so now let's see what happens once the logged in user logs out, right? Once the user logs out, then logon session in LSASS is destroyed. So no longer you can steal a token from an existing process because there is none. So instead, what we will do, we will run as utility in a particular network-only mode. So that's little known that you can run this utility and say what username and what password should be used when authenticating to remote servers, right? So we will still run as system user, but for the purpose of network authentication, we will use some fake password and username. Of course, it's the fake password. We don't know the real password of the user. And we have this run as session on a separate TCP port. So obviously, if we just try to authenticate to any domain server, it's not going to work, right? We don't know the password. We gave it some fake password. So obviously, that's not going to work. Now, what we'll do, we will use the credentials, the encrypted credentials that we have collected previously, and tell our injected DLL to actually use them for any authentication attempt. So it works by copying this captured encrypted secrets to this particular magic name. So now we tell LSASS, use this captured encrypted credentials. And now if we try it again, then it works, right? Despite the user has already logged out, we can still use the captured encrypted credentials to authenticate. So again, we don't know the password, we don't have password hashes, but still we can authenticate to remote servers as this user, even after the user has logged out. Okay. There is one more problem which I have left purposefully for later about credentials during login, right? Because there is a problem that somehow these unencrypted credentials must be somehow initially delivered to Credential Guard, right? Via this protect credential RPC. So it means if an attacker is present when the user is logging in and the user uses password-based authentication, it's enough to just run keylogger, right? And you will capture the clear text user password, right? And again, all this setup does not prevent it. If we use smart card-based authentication, then still the key distribution center sends password hashes during the logon, and again, they can be captured before they are deposited to Credential Guard and encrypted. And this particular problem about clear text credentials being available in root partition during the login can be taken care of with the help of more complicated configuration. So what you need for that is Credential Guard with armor key protection and smart card-based authentication. And it's more difficult to deploy, and in fact, it requires TPM, because without TPM, it doesn't make much sense. So how it's supposed to work? In this configuration, there's another key named machine key, right? This key is specific for a given machine, and it's available only to Credential Guard, only to this VTL1 protected VM. And the responses from KDC that carry authentication material like hashes or tickets are encrypted with this machine key. So because of that, even during the logon, the plain text authenticators never show up in the clear in the root partition. Root partition can see them encrypted with machine key, and it's only Credential Guard that can actually have access to them. So that's nice. That resolves this problem about credentials during logon. But even in this configuration, the same problem remains that attacker can still interact with Credential Guard and have it perform all single sign-on supported authentication for remote resources, right? Again, the problem is that it's difficult or impossible to tell that differentiate from the legal process of a legal user and process started by an attacker, right? And also there is no reliable way to deliver user has logged out, so forget all the credentials, refuse future single sign-on message to Credential Guard. It's simply not doable. Okay, so short summary in 2 words. Without Credential Guard, attacker can collect password hashes and use them later to authenticate to remote servers anytime from any machine. If Credential Guard is deployed in its hardened configuration, then still an attacker can collect encrypted password hashes and then again use them to authenticate to remote servers, just as before. But he has to do it from the same machine that these credentials were collected, right? So he is restricted to the same infection point. Whether it's easy for an attacker to adapt to this new condition and like start all the lateral movement from the same machine, it might depend on the precise scenario, but anyway, it's good to be aware that again, Credential Guard does not prevent using the credentials on the same machine. And again, we didn't need any sort of hypervisor compromise, right? It's all how Credential Guard is supposed to work, how it's designed to work. Okay, so now topic number 2, hypervisor-enforced code integrity. So Windows 10 can enforce code integrity of user mode binaries, user mode scripts, and kernel mode code. And the latter is done with the help of VBS. And we focus on kernel mode case. And the goal is ambitious. We try not to allow execution of any unsigned code in kernel context in the root partition, even if the kernel has been compromised already, right? So that's interesting. And the basic idea is that, again, the root partition's kernel no longer can decide which page is executable or not. It has asked VTL1 for approval. And this code running in VTL1 will agree to grant execute rights in EPT tables of the root partition only for pages that store signed code, right? So it won't assign execute permission for anything else. And there's another requirement, no such page can be both writable and executable. Because if you allow signed code to run and it is in a writable page, then an attacker could just overwrite it with something unsigned, arbitrary, right? And it would still run. So that's the basic idea. And there is a problem with this basic approach, at least in the case when we mix signed and unsigned code. So the common configuration is that unsigned user mode code is allowed, but unsigned kernel mode is denied, right? It's pretty common. So now let's see what happens in this scenario. User mode wants to execute some unsigned code at some location C. So because of the policy, it's allowed. So VTL1 must grant execute right for this location in the EPT table. Now user mode switches to kernel mode and jumps to C. And we have a problem because, again, execute rights have been just granted, right, in EPT. So it looks like C will be executed in kernel mode and it's unsigned code, so that looks like policy is broken. And this problem has been discussed in the SecVisor paper, academic project. The basic idea is that you need 2 separate EPT tables, one for code originating from signed and the other from unsigned pages. Additionally, root partition must be configured so that any attempt to, by unsigned code, user mode, to enter kernel mode results in VM exit. So hypervisor is invoked and it has a chance to change the current EPT table. And that essentially takes care of this problem. So let's see what happens. User mode wants to execute unsigned code at C. Great, it's approved. C is marked as executable in EPT. Now user mode switches to kernel mode and now something new happens because it's prevented from happening automatically. Instead, hypervisor is invoked and it changes the current EPT table. So now code tries to jump to C and now it won't work, right? Because we have changed EPT table to another version and execute right was granted only in this previous one, right? So at this moment we are running with a different EPT tables without execute right for C, right? So this problem is taken care of, and it's essentially, it's not stated anywhere in the documentation, but essentially Microsoft reused SecVisor ideas. There's interesting side effects that all this has on kernel exploits. So attackers love arbitrary code running in week 0, right? Because it's the most flexible thing. SMEP was a problem, but there are natural bypasses because essentially, once you have compromised the kernel, you can turn off SMEP from within the ROP payload, this way or another. But it's not going to work with kernel hypervisor-enforced code integrity. There is no way to turn off or turn on executable writes from within the kernel, right? So that's pretty nice. Also, there's another thing, you cannot hook kernel code, at least directly, by means of overwriting the kernel code with some hooks, right? Again, kernel cannot itself overwrite its own body, right? It has no power to do that. It doesn't mean that no exploits are possible. Quite the opposite, data-only exploits or ROP-only exploit are still fine. But nonetheless, that's annoying. I wonder, is there any way around it? Again, there is no way in which we can get a page which is both executable and writable, right? And we cannot use it to store our content there. We cannot create such new page. But perhaps there are some such pages left from the primordial Big Bang or boot phase. And it looks like it. So again, if you just scan the whole EPT table for the root partition, you can find some pages with RWX permission in it. I don't have a good explanation why they are here, for what purpose. My best hypothesis is they were needed for some early boot phase, for running some UEFI code. And for whatever reason, they needed this RWX permission. But still, you can still use them. An attacker can find them by probing each physical page for write and execute in ring 0. That's easier said than done. It's quite non-trivial. Anyway, I was able to run the utility that does exactly that, probes each physical page for being writable and executable. And as you can see in the output, most of the pages are indeed not both writable and executable, but there is at least one large contiguous physical address range which is writable and executable. This utility precisely tested by writing to this page and then executing it. So I reported that problem in Microsoft like at the beginning of this year, and they fixed it in this Microsoft bulletin in May. Okay, so let's start another topic, Hyper-V security. One important thing to be aware of that we have a very unusual threat model here, because there are a lot of publications and literature about hypervisor security, but almost all the time the threat model is that there is some VM, usual worker VM, without, for instance, direct access to hardware, and we try to protect hypervisor against attacks originating from these unprivileged worker VMs. Particularly without DBS enabled, root partition is kind of trusted, right? For instance, it can compromise Hyper-V in a number of ways, and it's not a big deal, right? Because usually you don't think that this management domain is where the attacks can originate from. And with DBS, it's different, right? This time the threat model is precisely that the root partition has been compromised. So as you can imagine, again, it's totally different from any other hypervisor security topic, and much more difficult. So even to start thinking about securing hypervisor against root partition, you need three things. You need secure boot, because without it, root partition can just use a Trojan version of the bootloader and Trojan version of the hypervisor, reboot, and then it will run with a custom hypervisor, right? Again, it's because root partition can mess with boot process, right, by specifying bootloader, etc. No normal VM can achieve it. Still beware that there were many vulnerabilities in the past allowing secure boot bypass, so you have to be aware of that. You need VTD, because without it, so VTD must be supported by the hardware and enabled by the firmware, exposed by the firmware, because without it, even with CPU protection, still the root partition can override hypervisor via DMA transaction, so use hardware to override hypervisor memory. And finally, you really need TPM, because it's needed to secure S4 process, as you will see below. Okay, so assuming we have it, let's see again what are the root partition privileges that are unusual, like in a sense they don't exist in normal VMs, And these privileges might be dangerous and they potentially can be used to attack the hypervisor. So obviously the first thing is access to privileged hypercalls. So there is a document named Hypervisor Top Level Functional Specification. And in there are 14 hypercalls usable by non-privileged VMs and 67 used from the root partition, right? So obviously much more code is exposed to the root partition. And more hypercalls exist entirely undocumented. Even more interesting part is that previously all these privileged hypercalls were not considered to be an attack surface, right? Again, they were usable only by the root partition, which used to be trusted, but now the situation changes, right? So Microsoft had to essentially harden all the usage of this privileged hypercall, so no harm can be done against the hypervisor. And there exists at least some potential possibility that they missed something, right? So definitely that counts as attack surface. What else? Root partition has access to almost all physical memory range. So obviously it cannot access the pages which are allocated for hypervisor and VTL1, because that would be direct bypass. Also local APIC and VTD bars are not accessible. Again, if they were, that would constitute easy bypass. But other things are accessible. So particularly chipset and PCI devices memory mapped I/O is available. And that will be useful. As well as ECP NVS memory region. So some memory region reserved for the usage of UEFI is still available from the root partition. I/O ports. So again, no normal VM has ever access to physical I/O ports, right? And in case of root partition, it's different. All are available with some exceptions that are known to cause problems. So like port 32 and 33 can be used to disable interrupts. So we don't want root partition to be able to do that. Port hex 64 can control a 20 gate setting, and again that's dangerous. Ports CF8, CFC are used to access PCI config space, and obviously Hyper-V does not like to grant root partition direct access to mess with the PCI config space. And the most bizarre one is port 1804. It is an I/O port that is used to trigger S3 sleep. So if it was exposed to the root partition, it could enter S3 sleep by its own, and that would be very dangerous. So these are the known ports that cause problems, and they needed to be removed from access by root partition. Model-specific registers are also relevant because some of them have interesting semantics related with hardware, but essentially none of MSRs are directly usable by root partition. So that's not very useful. Okay, so by using these privileges that I have described already, what mischief can be done, right? And the first problem is that the region to MMCFG region is not denied, right? So MMCFG is region of physical memory address space, and it's configured by the chipset so that whenever CPU accesses that, it is translated into PCI config space accesses, right? So there is one method to access PCI config space by these I/O ports, and this is, protected by Hyper-V. But this method, by using memory mapped access, is not restricted in any way. And what mischief can be done with it? Obviously, by accessing PCI config space, you can access and change device-specific register, including the chipset. And there are very interesting registers in there. For instance, remap limit and remap base register, which are again in PCI config space, can be used to create physical memory aliases. So you can configure them so that two different physical addresses actually refer to the same location in DRAM. And that essentially allows you to break any hypervisor security. Fortunately, it's a well-known attack, and these registers are locked, right? So even though they are accessible, they are locked by the chipset. It's possible that there are other interesting ones which I am not aware of. What else can be done with this config space access? You can change memory bars location, right? So you can configure a PCI device to claim the memory access cycles that are targeted to a particular address. And the idea is that you can kind of overlap, for instance, RAM, normal memory, with PCIe memory, right? And you hope that this RAM is somehow important for the hypervisor, and if instead of accessing this RAM, you access PCI memory, then some malfunction can happen. But as far as I know, that's not going to work. It is kind of explicitly stated in Intel documentation that you cannot, PCI device cannot claim cycles which are targeted to RAM range. Which is a shame, but is there anything else that we can try to overlap or cover with memory range assigned for PCI devices? And there is one, namely VTD bars. So again, VTD bars is the memory range which you use to configure VTD engine that is used to control DMA accesses. And this screenshot is from Linux because it's easier to explain, but again, it's less independent. So what we see here is, okay, we can figure out what is the address of the VTD bar. And if you try to read from this physical address, you'll get some output, particularly this location is the capability register of VTD engine. And originally, VGA device, integrated graphics, has memory mapped at this address, but we are going to change it. We will assign this memory address, originally used by VTD bars, and we will assign it to the memory bar exposed by integrated graphics. And what happens afterwards, if you try to read the physical memory of the same address, you get plain zeros, right? So by doing this, you deny all entities on the system, including the hypervisor, you deny it access to VTD configuration. And it's very interesting. Same can be done with the second bar. And I got pretty excited when I saw this, and I even started writing exploits for that. But it didn't work, unfortunately. The reason is that despite apparently you can create this overlap situation, and apparently read accesses are directed no longer to VTD but to this PCI memory, when you try to do write access, it results in hanging the platform. I do not understand precisely what's happening, right? But that's at least on two different boxes that was the behavior observed. Maybe it can be somehow, improved to actually work and do not hang the platform. Okay, problem number 2, other chipset registers. So still, there are other memory mapped regions, like in MCH bar region, and there are literally thousands of registers in them. And these are very fragile registers that, for instance, are related to handling of physical memory or controlling DRAM. And again, most of them are entirely undocumented at all. So that a question arises, are all of them locked properly? Are all of them lockable at all? And does firmware actually lock them, right? And if not, anything evil can be done with that? I don't know answer to this question. Again, the problem is that there is some undocumented functionality that we don't know the full semantics of it, right? And still, the root partition is granted full control over it. So that's, again, at least a potential problem. Another problem is S3 sleep, right? So generally, S3 is very fragile from security point of view. Because what happens is that hypervisor loses control, right? CPU is powered down, and then you have to kind of trust that the firmware does the right thing. So first of all, it maintains its own integrity, and then hands off control to hypervisor during the resume in an expected manner. And there was a vulnerability found in 2014 by me and Corey Kallenberg, as well as simultaneously by Intel guys, that are perfect for the purpose of taking control over the hypervisor, right? You could corrupt the resume process so that arbitrary code has been run before hypervisor was resumed, right? So this is all patched by now. So assuming you have all patched your firmware since 2014, that's not an issue. But there are more potential attacks against S3 thinkable, right? Again, see the white paper. And again, it's not entirely not a concern in normal hypervisor scenario when you have unprivileged VMs. Unprivileged VMs have no way to tinker with S3 process anyhow, right? It's only a problem with the root partition. S4 sleep is even more fragile because now what's happening? The state of the system is stored in a file, in a hyper file, and this hyper file is written by the root partition, whom we do not trust, right? So how it's handled under VBS is hyper file is encrypted. It's generated, its content is generated again in VTL1 in a secure environment, and it's encrypted in memory, and only the encrypted version is passed to the root partition to be written out to disk. But then you need to keep the key secret, right? This encryption key for the hyperfile, and it still needs to be available for the hypervisor and for the WinResume EFI application. So if TPM is available, it's doable. The key is sealed to TPM. So only if the platform is in expected state, meaning WinResume EFI is running, only then this key can be read from TPM. And that's good. But if there is no TPM, then we have a problem, right? So Microsoft tried to do the best they could. So without TPM, the key is in clear text in UEFI variable, and this UEFI variable is marked as boot only. So after the boot is completed and you try to use legal exposed interfaces by the firmware, this variable is not visible, right? Not even readable. But the problem is that the storage for the UEFI variables, so SPI flash, is inherently readable by the root partition. It's memory mapped just below 4 GB boundary. So all you need to get the key is just scan the memory under 4 GB, search for this particular UEFI variable name, or even better, for this magic constant, that is the beginning of the contents of this variable, and what follows is the clear text key package used to encrypt the hyperfile, right? So it means without TPM, S4 is insecure and can be used to take control over the hypervisor. So again, it's not, I haven't seen that remark in documentation about Credential Guard and VBS at all. Okay, and finally, the topic that everyone was expecting, so SMM. Again, it's mostly well-known content just for completeness and for some nice screenshot. So again, SMM is highly privileged mode of CPU, totally unrestricted by hypervisor. The problem is, nowadays firmware vendors pack quite a lot of functionality in SMM. And these services can be invoked by write to IO port B2. Again, the problem is that a lot of bugs in SMM has been found both recently and some time ago, but recently some of these problems got more attention even by more mainline media. So you might have heard about this ThinkPwn vulnerability found by Dmytro Oleksiuk, really some spectacular findings. So we have to live with it. We have to assume that SMM code can be buggy. And again, it's well known that SMM vulnerability can be used to compromise a hypervisor in runtime, right? Again, SMM code is not restricted anyhow by the hypervisor. Unless you use STM, but nobody uses STM and it's not going to happen anytime soon. So anyway, SMM vulnerabilities are fatal. Also, you can bypass secure boot as well if you have SMM vulnerability, but it's optional. And now what? It turns out that VBS allows direct access to IO port B2 for the root partition. So the root partition can invoke SMM services directly, as well as VBS grants access to ECP and VS memory region. And it's important because quite a few SMM vulnerabilities were exploitable by corrupting this NVS memory region and then invoking some SMM service. So again, what it means that it's expected that almost all SMM vulnerabilities are freely exploitable from the root partition, right? And it has been already demonstrated a couple of times, like Intel researchers have made a video in which they search by using power of SMM, they are able to search all the memory and just pattern match looking for password hashes, right? So despite the VTL1 memory is not reachable from the root partition, right, because hypervisor protects that, still SMM is all powerful and it can read this memory directly and particularly extract clear text password hashes. So I tried to show something more delicate or subtle or more VBS specific. I will show you the screenshots that show hooking the hypervisor in runtime, injecting code within it. So what's there? Again, we see LSA ISO is running on this test box, so Credential Guard has been enabled. And I wrote this utility that exploits some old and patched SMM vulnerability. It's not very important what's the nature of this vulnerability. Again, it allowed me to run arbitrary code in SMM repeatedly, as many times as I wanted. So if I pass this scan command to this utility, it searches all physical memory for VMCS regions. So VMCS page is the page used by the hypervisor to store information about both the hypervisor and VMs. So you can see this scan found 32 lines, meaning 16 VMCSs. And again, what we can read from this VMCS page is we can read the virtual address of the VM exit handler, right? It's within the hypervisor body. We can find what is the CR3 used by the hypervisor and other things like EPT pointer. You can see that there are two different VMCSs displayed here, and in fact they are for two different VMs. You can tell it because EPT is different, right? And one of these VMs is for the root partition, one of them is for VTL1. If you can tell by this number which one is which, just grab me after the presentation. Okay, so what code we will try to inject? Just this. I made some framework in which you can compile C code into DLL, and then my code will take care about locating that and creating hooks, etc. So what does this code do? It reads the VM exit reason, and if we are running because CPU ID instruction has been invoked, and if some register has some magic value, we just change this register, right? Just as a proof of concept that it works. So if you still remember what BPNOC utility was doing on Bluepill system, that's essentially the same idea, right? And again, does it work? So again, in order to hook, we need to know the physical address of the VM exit handler. So again, we take two pieces of information from VMCS, the virtual address of the VM exit handler and the CR3 register. And again, by using the ability to read any physical memory, you can walk the page tables of the hypervisor and figure out that the physical address storing the VM exit handler is there, right? And you can read the beginning of it. You can see that it looks like x64 assembly. So what do we do next? We run this magic CPU ID exe utility. It just executes CPU ID instruction with the proper value in R13 register. And what does it say? That before CPU ID, R13 has this magic value, and after CPU ID instruction, it still has this magic value, right? It's expected because Hyper-V doesn't change R13 register when emulating CPU ID. Okay, and finally, we use this hyperhook command to actually override the hypervisor body with with hooks and also place DLL in an expected location. And afterwards, if you run this magic CPU ID utility, so again it says before R13 was this magic value, but afterwards it was changed, right? So that shows that indeed we are able to alter the behavior of the hypervisor, right? We run arbitrary code in the context of it, and we can change any aspect of hypervisor functionality. And this is all in runtime, right? So that's very powerful. And again, if you control the hypervisor, you can do many interesting things. You can, for instance, monitor the behavior of Credential Guard. You can see what VM exit it generates, etc., etc. So again, that shows that SMM vulnerability can be used to totally subvert all hypervisor security. And that's pretty much it. So summary, despite its limited scope, VBS is obviously useful, right? So it blocks some attacks which are straightforward without it, right? So it's useful. But again, beware of the limitation, right? Beware about the design. Again, obviously, a lot of effort by Microsoft has been devoted to make it as secure as possible, right? But still, they needed to make some trade-off to maintain compatibility. And still, there is some very unusual attack surface. Particularly, the exposure of a lot of hardware access to root partition is worrying, right? There might be problems with that. Definitely, you strictly need VTD and TPM in order to secure Hyper-V. Again, you may infer from Microsoft documentation that VTD and TPM are kind of optional, right? Nice to have, but optional. And it's the other way. It's strictly necessary to maintain security of VBS, along with secure boot, of course. And still, SMM vulnerabilities are the greatest threat to this setup. Again, they are not very uncommon. They happen all the time. It's true that it's potentially more challenging to exploit SMM vulnerability, and they are specific to a given firmware make, right? But for instance, in case of this ThinkPwn vulnerability, all the line of all the laptops by the single vendor was affected, right? So it also happened. So again, this is a problem, and again, there are known examples to use SMM vulnerabilities to totally break any VBS security promise. Okay, that's about it. We have some time for questions. Anyone? It's an interesting question. So the question is, does root partition has access to TPM? I'm not sure, because when I tested it initially on Windows 10 initial release, so threshold 1, I could see that indeed root partition was given direct control of the TPM, right? But I'm not sure if it's true in the later releases. But still, even if it does, what would be the possible impact? How would you use it to actually compromise the hypervisor? Just ability to access TPM, I am not aware of any direct attack that could be used to compromise the hypervisor. Say it again?
If that's true, then the root partition could decrypt the sealed key that encrypts the hypervisor.
That encrypts what? Yes, but it's assuming Microsoft did it properly, so after reading the key, it changes the PCR values, right? It's no longer possible, right? If the encryption key is sealed to particular PCR values, meaning particular state of the platform, then it's not possible. I haven't checked that. I assume they did the right thing because it's more or less obvious, right? That you need to do that. Say it again.
You research 2012 R2 and beyond for the same thing in virtualization?
Research Windows what?
Windows 2.12.
To 12. No, I didn't. I just focus on Windows 10 because, again, I'm mostly interested in client-side security solutions, so that's my main field of interest.
Okay, thanks.
Are you familiar with SGX? And can you hear me? Oh. If you're familiar with SGX, if it's a complementary architecture or a contestant?
Say it again?
Is SGX a complementary architecture or contestant to this?
Complementary and contestant. I don't think you could implement same things with SGX. Maybe Credential Guard could be used for that. Yeah, you have some sort of trusted code, right, and only release secrets. That's an interesting question. Maybe SGX looks much more reliable, right, because again, it just carves some memory and runs code protected from everything else in it. And you have some guarantees that it cannot be tampered with. So at least Credential Guard, I think, potentially could be re-implemented using SGX. But for instance, other things like code integrity, I don't see how it could be done, right? Because it requires some external control over the kernel, which can only be done by a virtualization and EPD table. So yeah, I think Credential Guard could be implemented with SGX, other features likely not.
Thank you very much.
Hello.
Well,
In your first example on the encrypted token for the single sign-on, there's absolutely no TTL on that at all. Is that something that can be configured?
with absolute no what?
On the session token for the encrypted token that you get, the session token, right?
Yeah.
When you're doing the replay?
I haven't seen it expire anytime. Yeah, that's a good question. They could add it, but then if they added any TTL or expiry time, it would mean that in case of legal user, right, using it, he would be prompted to relog in, right?
Yeah.
That kind of impacts usability. Same is about Kerberos tickets, right? TGT has expiry time, I think default 7 days. So after that, user needs to relog. And again, implementing this shortened lifespan of credentials might help. But again, it impacts usability and doesn't entirely solve the problem, right? Because if you have 2 days to start lateral movement, possibly it's enough to compromise the whole network. Right?
I'm thinking
It's not
3 to 6 hours, but yeah, thanks.
Okay. I guess that's it. Thank you.